Hey everyone. So welcome to this lecture on vector databases and semantic search. Now this is part of a series where we're going to be exploring vector databases in a little detail, right? And so this is the first lecture, but the idea is it's going to be complete in itself. And what we're going to do is we're going to explore what a vector database is, why it's important, how it works, what semantic search is, look quickly into vector embeddings, and do a practical example, right? In Python, where we're going to actually kind of use the API to a vector database, connect to it, and see how you can quickly kind of, work with one. So you should kind of, at the end of this lecture, you should, or this video, at the end of it, you should have a fairly good understanding of what a vector database is and how to get one to work. And then in the next few lectures, we'll then explore some of the algorithms in more detail, explore another application. And so, you're here because you've heard the term vector databases. They've really become, extremely fashionable of late. And whether you're trying to build, uh, an app or a tool to kind of search, kind of, kind of set up smart search on your local machine for all your files, you're building the world's next Google, right? A really smart AI-powered search engine, or you're building an LLM app. Vector databases, are kind of a crucial component of, all of these systems. So, what is a vector database? Well, simply put, a vector database is basically a database designed to very quickly and efficiently store and retrieve vectors, where what you see here, these numbers, this collection of numbers is an example of vectors, right? So this is one vector, this would be another vector, this is another vector, and so on. And a vector database is a database that's designed to efficiently store and retrieve these. So why would we want to do that? Well, over the next, few minutes or so, we'll explore what a vector is, what are vector embeddings, another term you've probably heard of. Then kind of that'll take us naturally to the idea of semantic search. We'll explore, how a vector database basically functions, and then we'll kind of do a practical example in Pinecone, right? So let's start with the idea of what a vector is. Now, what you see here are examples of the vector. They're the same vector written in two different forms, right? And so a vector is basically a mathematical entity which can be represented or written as a collection of numbers, right? So each of these is called the element of the vector. And these vectors are basically representing, in this case, a mathematical entity, in a more general context, the state of a system, right? And they are designed in such a way they're supposed to follow rules of vector algebra. Now, we're not going to worry about vector algebra in this lecture too much. We will have kind of a follow-on lecture where we start delving into the algorithms, and there we will kind of explore vector algebra in a little more detail. You can think of a vector as a simple example is a point in a coordinate system. So you have the simple x and y axis. Let's say you take a point here, which is 3 on the x and 2 on the y axis. And then if you draw a line from the origin to that point, you can treat that point as a vector in this coordinate system, right? And the line kind of going from the origin with the arrowhead pointing to that point is a good way to represent that vector, right? So it can be represented as a point in a coordinate system. So this is a two-dimensional coordinate system. You can think of this, the V here, as a three-dimensional vector, right? A vector in a three-dimensional coordinate system. Now, the number of elements in the vector is basically the number of values here. So in this case, it would be 3 for this V. A vector has magnitude, which is effectively a way to kind of understand, say, the size of the vector, right? So in this particular case, it's basically represented by taking the sum of the square of each element and then finding the square root of that. So in this case, it would be 2 square plus 3 square plus 1, which is 9 plus 4 plus 1, right? Which is 14. The square root of that is the magnitude of this vector. The same thing you can do here. It's 2 square plus 3 square and the square root of that. So it would be 4 plus 9 and the square root of that, right? What a vector also has, apart from a magnitude, is a direction. So a vector in mathematics and also in physics, it has a direction. So in this case, it's going from the origin to that point. This is the basic idea of what a vector is from a mathematical standpoint. Now, a really important application is in physics, in geometry, and so on. So take an example of this aircraft here. You have this aircraft that's just taken off from this runway, and let's say the point it took off from, we're going to define a coordinate system there. Now, just bear with me for a minute. The lecture is not on physics, but just to give you an idea how you can use it. Now, you have this aircraft here that's taken off from this point. If you want to understand where the aircraft is, let's say it's now flown 500 kilometers in the x direction, 30 kilometers in the y, and it's flying at a height of 9 kilometers, right? So that's the distance it's covered. You can represent that as a position vector, right? And in this case, the units is kilometer. I'm not writing the units here, but you can represent that as a vector, and it becomes the position vector of the aircraft. And as the aircraft moves, the position vector changes. So at any given point of time, you can have a position vector for the aircraft. The aircraft's also flying fast. So you can think of, kind of the movement of the aircraft, which is called the velocity, as another vector. It's moving at 800 kilometers an hour in the x direction, 15 kilometers an hour in the y, and 1 kilometer an hour in the z direction. And so that would be the velocity. How is that different from the speed? Well, the magnitude of this would be the speed, but the velocity is basically a vector because it's got a direction. And in this case, it's three-dimensional because the aircraft can move, in two dimensions this way, and then it's also got the height, right? And so that's kind of an example of where you'd use a vector in physics, and this could then be used in calculation. Right? It's not just physics. You can use a vector to represent the state of any system mathematically. So let's take the weather, right? Again, it's a kind of a physics example, but let's say you want to measure the temperature, humidity, wind speed, wind direction, pressure, precipitation, and cloud cover at different points in the atmosphere. You can treat that as a vector, right? And you can collect those values. And then what you can do is, I'm taking out the units, and you can just write this as a vector. You write that at different points in the atmosphere, at different points in time, and they can each be a set of vectors. So it's a way to define the state, and then you can run math or run a machine learning model on these vectors. So a different example is, let's say you have a medical record of a patient. And so at a given point, you're measuring his heart rate, blood pressure, temperature, oxygen saturation, and glucose level. You can write that as a vector as well. You can say, well, these are the values. And I'm just making these up, right? So you have these values and you take out the units, write this as a vector. And that's the state of that patient at that point of time. You can have the patient state at different points of time. You can have this for different patients. And that would be a way to kind of take the patient's medical condition, convert it into a vector, right? And now you can use that vector either as a way to just record his or her condition, but also as a way to run math, right? Or mathematical operations, machine learning models on this, because machine learning models and deep learning models understand numbers, right? They don't understand text. So you're starting to see how vectors are actually not just used in physics or pure math. There's a lot of application to this. Now, that brings us nicely to the idea of a vector embedding. With, deep learning models and machine learning models becoming very powerful, with becoming, improved models coming in, large language models, and so on. The whole idea or the whole part of these models is they can handle unstructured data. What do we mean by unstructured data? So there's text, there's images, there's audio, and so on. These are unstructured data or objects, right? How does a machine learning model understand these, right? It doesn't understand these in the state it's in. What's done is these are converted into vectors. So all three of them are not the same vector. This is just an example of how these can be converted into vectors. And this vector that is representing this object, whether it be some text, it be an image, it could be some audio, is a vector embedding. And the model used to generate this is an embedding model. It's typically a machine learning, mostly a deep learning model, right? That's used to kind of convert these into vectors, right? And they're different for different types of unstructured data. For text, it would be a transformer-based model. For images, it would be a convolutional net, and so on, right? And so once you have a vector embedding, right, meaning you've converted this unstructured data into a vector, now you can feed it into a deep learning model that understands the numbers, right? And now the model can actually understand what actually is being passed to it, what the context of the data is. So the reason vector embeddings are used is because the way they're designed or the way they're generated, because this is not representing a natural system. It's not representing the position of an aircraft, which is an actual set of values, right? It's exactly where the aircraft is. You're coming up with a machine learning model or a deep learning model that takes this and gives it a meaning, and that meaning is represented by this vector, right? And so the algorithms, the embedding models, are designed in a way that ensure that they capture context or relationships in this unstructured data. So let's look at an example, right? Because kind of vector embeddings, the reason, one of the big reasons to have vector databases and why they've become so popular is because they're used to store vector embeddings, right? So let's look at an example. Let's take three words: cat, mat, and dog. Now, let's say you have mat and dog, and cat comes in, and you want to see which of these words are related, right? So if you look at cat and mat, right, you say the at matches, whereas with cat and dog, there is actually no match in terms of letters. So if you look just at letters, you'd say mat has more in common with cat, right? Dog is not really related. However, let's now compute a vector embedding. So we're using this algorithm called glove, right? And I'm not going to go into detail on how glove works. That's for the NLP course, natural language processing course, that will come up soon. But you can go check it out here at nlp.stanford.edu/products/glove. It's a statistical machine learning model that can take words and give you a vector embedding, and it's been trained on a large corpus of data. So it tries to it's able to, or it's got the context of these words embedded in it in the form of the vector. So what do I mean by that? Well, if you pass in cat, it's going to give you a vector that looks like this. You pass in mat, it's going to give you this vector. You pass in dog, it's going to give you this vector, right? But there are other algorithms that can do the same thing. Word to vec is another example of an algorithm. I've just used glove. It's very easy, and you can get it as a library as well. So you can just download a file that's got the word and the vector embeddings. You can load it as a dictionary, not a library, a dictionary in Python, and you can get the embeddings. So you get these vectors. Now, what we're going to do is we're going to try and see how it captures context, right? First. So we're going to use a technique called principal component analysis, where it's going to take this vector that Glove has generated for us and break it down into a two-dimensional vector, right? What it's doing effectively, we're not going to principal component analysis in this lecture in detail. We'll do it later. But it's basically kind of converting this large 100-dimensional vector into its two main components, right? That capture the essence of what was there, right? And so we can do that for all the words, and we've created this. We've run this right now for all these words, and it's going to convert it into these 2 points, which means we can now plot it, all the words on a two-dimensional plot. There's another approach called the TSNE, which you can use as well. I've just used principal component. And so you see, when we take those words we had and kind of convert it into a vector, you see that words that are related, even though the spellings are so different, cluster together. You see the animals clustering together. You see cat, dog, tiger, lion, elephant, cow all together. You see the fruits and vegetables together. You see carrot, mango, and so on. You see, inanimate things, stapler, bed, pillow, mat. These are all related. You see them together. And so you see mat and cat are so far away, right? You see electronics showing up together. You see keyboard and laptop showing up very close together, which means when glove has been trained on data, it's found that keyboard and laptop show up in contexts that are related, right? Whereas keyboard and cat don't really do that. But what you also see, so let's look at cat, dog, and mat. Even though the spellings of cat and mat are much closer, you see that when you convert it into a vector embedding, cat and dog actually are much closer to each other. Mat is not really related, right? Or not really showing up a lot in context. So a vector embedding is able to capture context. This is an example of words, but the same thing applies to sentences, for images, and so on, right? You also see interesting things depending on the data that's trained and also depending on how you visualize this. But something like mouse is close to cat and dog, but it's also showing up kind of slightly away. It's also showing up close to electronics or in the direction of electronics, because a mouse also shows up in that context. You see apple, right? It's showing up so far away from fruits. Why is that? Because Apple can also be used in the context of electronics, right? The company. So you're seeing how these words are capturing some syntax, some context, right? Now, how do you compare these vectors? We've created this visualization, but you can't just plot this and compare it. There would be inaccuracies because you're reducing this 100-dimensional vector into two. So they're not I mean, just a good way to visualize it, but you need a better way to compare it. So if you just compare them element by element, how do you compare them, right? Doing just a string search or basically saying I'm going to compare each element is not really going to work, right? That would be the wrong way to do it. And so kind of comparing vectors uses an approach or uses metrics called vector distance or vector similarity metrics. And they measure how close vectors are to each other. So in this case, we've just kind of plotted them on 2 dimensions. So you can look at a 2 dimensional example. Now, one kind of distance metric that's used is called the Euclidean distance, which is basically just the distance between the 2 points. We said that you can look at a vector as a point in a coordinate system. So we were visualizing it in 2 dimensions. So it would have A and B would have 2 dimensions. If you're comparing the actual vector, it's 100 dimensional. So you would have to compute the distance, assume it's a 100 dimensional coordinate system. So you can't really visualize it, but you can think of all the different dimensions there. And how you compute the distance is basically by taking the square root of the the difference between you take the difference between each dimension. So a1 b1, so a and b are the points. A1 b1 is the first dimension, a2 b2 is the second dimension, a3 b3 third dimension, and so on. You square that, you add it up, and you take the square root of that. Now we'll see this a little more in future lectures, right? So in this particular case, it would just be a1 b1 square plus a2 b2 square, and the square root of that, where a1 and b1 you can have say 1 and 2 here and 3 and 4 here, for example, are numbers, and you just apply this formula. But it's basically calculating the distance between these vectors. And the vectors that are closer together, you'd say they are more similar, right? Another metric which is used more actually is the cosine distance. So what is the cosine distance? Well, if you have these two vectors, it's just measuring the angle between the two vectors effectively, right? So it's saying vectors that are closer together in angle are better aligned and so are more related. Vectors that are farther away in angle are distinct, right? So this is what a cosine is. So given the angle, the cosine is, when the angle is 0, the cosine value is 1, which means when the angle here is 0, what happens? The two vectors are perfectly aligned, right? That's why the angle is 0. So when the angle is 0, it's saying the cosine is 1, which means when you use the exact same value, for example, you just compare cat with cat, the value should be 1. As they go further and further away, the value goes down and down and down. When they're 180 degrees, this is 180 here. When they're 180 degrees apart, which means they're in exactly opposite directions, the value would be -1, right? And so the larger the value, the closer it is to 1, the more similar the vectors are. The smaller it is, the farther away, and the closer it is to 0 or -1, the farther away the vectors are. So the actual metric is different in terms of how you look at it from Euclidean distance. In Euclidean distance, the smaller the value, the better, the closer they are. If you're using the cosine metric, the closer it is to 1, the better, the closer the two vectors are. The farther away it is, and the closer it is to 0 or -1, the farther away or the more dissimilar the vectors are, right? So these are examples of two metrics. There are other distance metrics as well, but these are two very widely used ones, and cosine distance is what we're going to try out now. So what are we going to do? We're going to take cat, dog, and mat, and we're going to say, okay, let's compute the cosine distance, right? So you can look at that expression and see how to do it. And in a future lecture, we'll kind of do some of the math a little more in detail. But I've already shown you the equation, right? So you can code this up in Python as well. So if I take the origin, which is here, so this line is slightly misaligned. Um, you say cat, dog, and mat, right? You see that cat and dog, the angle is very small, right? Whereas mat is farther away. So cat and cat, the cosine distance would be 1. Cat and mat, the cosine distance is 0.1, right? And we know that the farther away it is from 1, the smaller it is, farther away the words are. So this is quite far away. Cat and dog, much closer together, right? Cat and dog, much closer together. So we see how the word embedding is capturing the meaning. You could also use Euclidean distance and you see cat and dog are much closer, cat and mat. Now, this is obviously doing it in the 100-dimensional space. So this is just a representation, right? This is not really giving you the answer because the actual values here are in the 100-dimensional space. So you're doing it for the full vectors. You're not doing it for the reduced vectors. So we have a way now to compare vectors and see how similar they are, right? That brings us nicely to the idea of semantic search or similarity search. In similarity search, what you're doing is given some unstructured data, you're converting it into a vector, and then you're trying to see and find other vectors and so other data that's similar to it. So again, coming back to the same example, let's say we have these words. I want to say how close a rabbit is, or rather, I have a database with each of these words, and I want to say if I say rabbit, what's going to show up? Rabbit is not in this database at this point. So if you just do a string search, you're going to get nothing, right? Because there is no word called rabbit in this database. But actually, there might be words that are related to it. So what do? You compute the distance to rabbit using, in this case, I'm using the cosine metric. And I get, and I've just shown it for some of the words, you get the distances, right? Using the cosine metric. And then what do? You say, well, these are the three that are closest to rabbit. And so it's actually quite logical. Rabbit doesn't exist in the database, but you have cat, dog, and mouse. It returns these three and says, actually, these are quite close. It also is an example of how mouse shows up quite far away here in the two-dimensional projection, right, using PCA. But actually, when you compute the distance for the full vectors, you do see that rabbit and mouse are also quite close, which makes sense, right? Because, well, they're all animals. They're kind of similar, right, in the kind of animals they are. Lion and tiger a little further away, right? They are different from a rabbit. So you see how, using vector distances, you can find what are called the nearest neighbors. And so the way to think about it is rabbit would clearly show up somewhere here. And what you're trying to do with a similarity search is you're trying to find vectors that are similar, right? And so are the nearest neighbors in that vector space to what you're searching for. And so rabbit would first be vectorized. You'd get the vector for that and then compute this. You'd get the three nearest neighbors. Now, this applies to any kind of vector you do. So you have a document, you could break it into sentences, you could compute vector embeddings for those sentences, and then you could run a similarity search. And now, even if you type a search for text that's not really in the document, and this is kind of an example we'll look at, you'll still get things that are related. If there's something related in context to that document, you could get that out. Same applies for images and so on. Now, we've done what is called a nearest neighbor search. And again, we'll do this algorithm specifically because it's a very important algorithm. It's called the k nearest neighbors algorithm, where k could be 1, 2, or 3. In this case, we're saying 3. We're giving you the 3 nearest neighbors. Problem is, as you can imagine, if you have a billion points and then you had a query, you have to find the distance to the billion points in the database to get the nearest neighbors, right? Because it's a new point, you don't know how close it is to anything. So if you use an exact nearest neighbors, you're going to have to, for each query, do a lot of computation, which means if you're Google and Google is using semantic search, right? When you type something into Google, it's not looking for those exact letters, it's looking for the context. When you search for a product on Amazon, when you search for a song on Spotify, they're all using semantic search, right? So they're handling billions of queries, they've got trillions, billions or trillions of data points. You need something a lot faster than nearest neighbors. And that is where approximate nearest neighbors method come in. And as the name suggests, they're approximate. What they're designed for is to be much faster, much more efficient, but without compromising too much in accuracy. Now, you can't get exact accuracy for higher speed. What you can do is get higher speed, but little compromise in accuracy. So there are a number of different techniques. An example of localized sensitive hashing. There's the highly navigable, hierarchical navigable small worlds algorithm, which is one of the key algorithms used in vector databases. You've got Annoy. Then there's FACE, which is an open source library that Facebook has given out, which has some of these algorithms, and you can use it to set up, semantic search very quickly. And so using an approximate nearest neighbors, what happens is, and the reason I'm explaining this is because that now brings us very quickly to how a vector database works. So looking at localized sensitive hashing, what you do is you effectively, and again, we'll cover this algorithm in detail, but the basic idea is given a vector, what you can think of is what the algorithm is doing is it's going to basically You're going to have a set of classes or a set of groups that the data is grouped into. What it's going to do is convert that vector into one of those groups. So we're going to look at those groups as buckets. And it's going to say, okay, this data point, the algorithm is going to say, well, actually, it falls in this bucket. Ideally, one bucket, but could look at more than one bucket when you query it. So it's going to take the data you have, so cat, dog, mat, and so on. It's going to take each of these points and put them into buckets. You can think of the animals in one bucket, you can think of the fruits in another, and so on. Now, when you query it, when you ask for rabbit, it's going to again use this algorithm and see which bucket that query would fall into. And then it's only going to search in that bucket for the nearest neighbors, for example, right? And so that is a way to speed things up, because when you're starting off, you put your data in, it would first create these buckets and know which data points are in these buckets. And then when you query it, it only looks in the relevant bucket, right? Which means the search is a lot faster. With HNSW, what it does is a slightly different approach. It creates what are called, these hierarchical graphs, right? What it's doing is at the lowest level, all the vectors are there. Then as you have more, it creates more and more levels, where at each level, it's kind of filtering away some of the points, right? So at the highest level, it's got only a few of those points. When you query it, so at each level, you have less points. And when you query it, so when you given the initial vectors, it's creating this structure. Once it creates the structure, when you query it, it starts at the highest level. There are very few vectors for it to find. And so, or rather search through. So it quickly gets to its nearest neighbor. And then that point now is also there at the lower level, right? At each level, it's got less and less points. But the points that are there at the lowest level are there at the level above as well. So this point exists here. It's going to find that point, say, okay, this is my closest neighbor. Let me go to that at the next level. Now it's going to use the graph of that point to find the nearest neighbors at that level. Once it does that, say it's this point, it's going to say, now I'm going to go to that point in the next level, see if I can further refine this prediction till it gets to the nearest neighbors, right? Or what it believes are the nearest neighbors. And then it's going to return those nearest neighbors. Now you can imagine this might go wrong. You start at the wrong point. You might end up at a different point that isn't necessarily the nearest neighbor. It's an approximate technique, but it's been shown to work very well. And so this is kind of the algorithm that's very widely used for vector search and in vector databases. So coming back to what a vector database is, a vector database, as we have said at the start of this lecture, is a way to efficiently store and retrieve vectors. What a vector database does is, instead of a typical database that uses, something like, conventional hashing technique or a B trees or something like that, to query and find what are called exact matches, right? So it's trying to find exact matches to your data. A vector database uses vector search or semantic search using an approximate nearest neighbors to find similar vectors in that database. And that's where it's different. And so for a database, indexing is the process of creating a data structure to allow you to quickly query the database, right? So conventional databases have their own techniques. A vector database uses an approximate nearest neighbors, typically the HNSW algorithm, right? And so an example of how that would work, you've got all this data, you want to feed it to the database. So for each of them, you create the vector. So I've shown it for cat, but you do it for all of them. Once you do that, you can then add not just the vector, but you can add some metadata. You can say, well, actually the text is cat. It's, for example, I want some metadata. I want to say what class it is. So it's animal and so on. You do that for each of these data points. And then you pass that into the vector database. So there's sometimes a pre-processing step to reduce the dimension. We've seen that it's a 100-dimensional vector. Now, sometimes vectors can be 1,000 dimensions or 500 dimensions. And you might want to speed things up a little more. So you can, in pre-processing, use things like product quantization, which will further speed up the search by reducing the dimension. We won't worry about that now. We'll cover that in a different lecture. But then you pass it to the database, which creates this indexing structure based on approximate nearest neighbors, and then stores the vector, right? And it does that for each of these points. You see the vectors stored, and you have this indexing mechanism. And then when you query it, so you ask for rabbit, you first convert rabbit into the vector, and then you feed that query in. So it would go into this indexing mechanism and find the nearest neighbors using this indexing mechanism, and then it would return the nearest neighbors. So it would return cat, mouse, and dog. What you can then do in a vector database typically is then further filter. So you can say, well, we added what is called a class, right? You can maybe then say, I want to check for class, and say mouse in your context is actually electronics. You can say class animal, and it filters out mouse, returns you cat and dog. So that's basically how a vector database works. It uses the approximate nearest neighbors to find you the closest vectors. So it's not looking for exact matches, which is what a typical database does. It's looking for similar vectors. And if the embedding mechanism you do is a good one, then it captures the context well. Then the vector database will give you really good similarity matches, right? So it also depends on the embedding algorithm you use. And the other thing with a vector database is it's a database, right? So it has to have all the properties of a database, which means you should be able to create, read, update, delete vectors. And when you do that, the indexing mechanism needs to be updated in real time, right? So you might have to reindex with the HNSW. Vector databases out there use smart techniques to ensure that very quickly it's set up the indexing for the new point or remove the indexing for the old point and so on without compromising performance. And also, these databases need to be hosted, right? They need to be scalable, they need to be concurrent, they need to handle concurrency, so multiple queries, and so on and so forth. So it's not just having an algorithm that you can build that you give it a set of vectors and it just creates this indexing. Because it's a database, it needs to be able to handle what a typical database does. Suppose it's the database that's supporting Google. You can imagine the number of queries, and as it indexes new data points, when you go and kind of indexing a new website, you can imagine how complicated this might be, and so how efficient the database needs to be. Now, the reason vector databases have really kind of come in vogue is because with large language models coming in and people trying to build apps to use large language models. So you've heard of retrieval augmented generation and so on. You need vector databases because language models don't understand language in text format, right? They use the vector embeddings. So when you type this into a language model, it's going in, becoming a vector embedding. That's what's being fed into the large language. Now, when you type something into a language model and it says, well, memory, what's the memory? The memory is storing these vectors, right? So it's storing your input, it's storing the output. And then when you ask it another query, a smart model like, say, a chat GPT would also reference its memory for what you've asked it previously, use that to create or update what is the prompt which is going to the language model. And the language model then kind of comes up with the response, right? It predicts the next set of words and gives you the response. So these models only understand vectors. So you need the embedding as well, the embedding model, but then you also need the database to store these vectors. So it serves as a memory mechanism for large language models. And if you're building apps that use large language models, like RAG apps, for example, you're building an app to store documents in vector format, and then when somebody queries it, you've got a book, you've got all your data, text data, right? User comments, user feedback, for example, in vector format. Somebody asks you a question, it needs to be able to query the vector database and then use that in conjunction with the large language model. And we'll have a lecture or two on RAG in detail. But basically, so the vector DB serves as the memory for these language model powered apps. There are a number of other applications that use, vector search. So semantic search we've just covered, and that, Google is an example of, where semantic search comes in. You type something and it doesn't give you, look for those exact words, it's looking for context. With image search, you use embedding models to convert your image into a vector. Now, instead of capturing just the features, or rather, instead of capturing the exact pixels of that image, it's capturing the features, right? So it would use a convolutional network, and it would basically, the vector would have the features, which means you can use it to find similar vectors or similar images. So that's how image search works. You can use this to kind of compare audio. Recommendation models in Amazon, for example, use embeddings. It converts product information and user information into embeddings. And then we've just looked at, retrieval augmented generation and memory for LLM. So a lot of applications, a lot of these fairly new, which is why the whole demand for vector databases. So there are a number of vector databases, and I might be missing a few. So please add them, if you're watching on YouTube, please add them to the comments. But there's Pinecone, which is quite famous. The C should be small. There's VV8, there's Milvus, there's Chroma, there's MongoDB, there's Quadrant, Elasticsearch. Some of them are open source, so you can go and download them, modify them, run them locally. Some of these are commercial applications, right? Okay, so we've understood and looked at a number of different vector databases. We've understood the theory, we've understood what embeddings are, what semantic search or vector search is. Let's do a practical example, right? We've understood the word embeddings part. Let's do a more interesting example. So we've got these two paragraphs. One is about matrices in mathematics, right? It's a mathematical concept. If you've been following the deep learning series, deep learning lectures, you know how or what matrices. There's also the famous movie called The Matrix. So you've got two paragraphs on that. For whatever reason you're familiar, you're interested in movies and you're interested in math, you've got this in your system, in your database. If you type in, tell me about the movie The Matrix, what would you get? Well, if it looked for a string search, this phrase itself does not appear here. If you search for just matrix, how does it know whether it's this matrix or this matrix, right? Okay, you can say capital and small, but assume that it's case insensitive. So, well, use vector search. So what do? You break, in this case, we're going to break this paragraphs into sentences. Typically, if it's a document, you break it into chunks, which would be overlapping sentences. We take each sentence and we use a sentence embedding model, which will convert that sentence into a vector. Once we have that, we convert it into this form where we have the metadata. In this case, we're keeping the full sentence, right, as the metadata. And we're adding an index, right? So there are different ways to convert or generate vector embeddings. There's sentence BERT or sentence transformers. Most of them use transformer. They're all transformer-based models. Some of them based on BERT. So this is available on Hugging Face. You can use, you can download, you can install it in Python. You can also use OpenAI embeddings. They're the E5 models, right, from Microsoft. And I'm going to use this because Pinecone has hosted versions. And we're going to do the example in Pinecone. So we're going to use the hosted E5 model. Just make sure that for what you store and for the query, use the exact same embedding model, right? As long as you do that, you'll be fine. So, like I said, we're going to use Pinecone as an example. It's hosted. It has a free trial. You can feel free to try any other database. I've just been using this, to stay consistent. So it's a very widely used database. You can go check it out at pinecone.io. What you need to do is create an API key. So once you sign up, you can go in and click API keys here and then create your API key. It's very simple. Once you create it, do not share this with anyone, your API key. You can use it to set up your app. And so we're going to go and build a quick Pinecone adapter. And again, Pinecone C should be small, but we're going to build a quick Pinecone adapter to allow us to take, the problem we've set up, right, which is those two paragraphs, convert them into embeddings and quickly query, right? So let's just open up. I'm going to using Jupyter Notebooks. We have a video on how to get set up with Jupyter Notebooks and Python on that. So I'll add a link to that. You can go check that out if you're not familiar with that. But let's just get started with the code. Okay, so let's now open up the Jupyter Notebooks. So if you're coding with me, you can open up your Jupyter Notebooks as well. So to set up Pinecone, you can go to the Pinecone website, and we've shown that in the notes, in the slides. And what you can do is, it's very easy to set up. So you can go check the setup part there. But if you know how to use pip, you can just say pip install Pinecone gRPC, right? And that'll get Pinecone set up for Python. Now, sentence transformers is optional. In this particular case, I'm going to stick to Pinecone. So I'm going to use the embedding models hosted on Pinecone. But typically, if you don't want to do that, you want to use sentence transformers, you can go and set up sentence transformers as well. And then what you can do is replace the embedding function that I'm going to write here, which uses Pinecone's hosted model. You can just replace that with sentence transformers, right? And it's very easy to get set up with sentence transformers as well. I won't be showing that here. When we do, sentence embedding models as part of NLP, we'll kind of look at that there, right? But if it's really essential, kind of drop me a note and I can add a quick section on that. So we're importing Pinecone gRPC, and what we're doing is importing serverless specs. So we're going to be running serverless mode, right? Which It's kind of a development from Pinecone that makes it very easy to get up and running, right? You don't have to worry about provisioning your server and so on. You just create an index and get going. And so let's just start by writing the adapter, right? So I'm going to say class Pinecone adapter, and then we're going to say just initialize this, right? Now, what do we want to do? We've got the API key, kind of showed you in the slide, you have to get an API key. So what I want to do is first load the API key. So I'm going to create a function called load API key as part of this adapter, right? And so let's just set that up. Let's say dev load API key, right? Um, right. And what we're going to do is we're going to say, now what I've done is stored the API key in a env.json file. And the idea is that when, you kind of extend this, let's say, to say include things like querying a language model like OpenAI and so on, what you can do is add more API keys. So it's basically a JSON file. And remember, if you're using Git, do not commit that file, right? Do not share it with anyone. But I'm going to open environment.json in read mode, right? So that's what this does. And then what I'm going to do is load the key. So it's just a file that has all my keys. In this case, there's only one key, right? It's the API key for Pinecone. And then I'm going to return, and in this case, because it's just the Pinecone API, I'm just going to return the Pinecone API key, which in the JSON file has got this name, right? This is the And so API key self.load API key will load this key there. And then I'm going to say self.pc, which is for Pinecone, is Pinecone. And I'm going to pass in, right, which is what we've loaded here. So that's the Pinecone client. I'm going to say API key is equal to API key, which we've just got from above. So that should get us started with Pinecone, right? Okay. Let's just see if this works. Let's just say PCH is Pinecone adapter, right? And let's just run that. So I haven't run this cell. Let's run all these cells and then say, and it says keys not defined. Because I've called it key. Let's rerun this. My bad. And that's run. So we're good. Okay. So we're good with that. What do we do next? So the first step is you've got data, you need to convert it into embeddings, right? So let's just set that up. Now like I said, I'm using the Pinecone API for that as well. And so I'm going to create a function in this adapter, right, that allows you to do that. Right? So Pinecone has two modes that you can run in. When you give an index, you can either generate your API, generate your embeddings, and then pass the vectors in, or you can use a mode where it's called the integrated mode, where you just give it the text and it uses its own model. You specify the model and it does that internally. But we want a general kind of implementation. So we are going to call the embeddings specifically. So how do you do that? You say self.pc, which is what I've created here. So it's the Pinecone client. And you call inference.embed. That tells us we want to generate embeddings. And what do you pass it? You have to pass it the data, but all we want to pass it, in this case, the data has an ID and text. Now the ID is so that when we index this, create an index, you need the ID. But actually you need the embeddings only for the text. So first you specify the model, and we're using the multilingual E5 large, right, which is hosted and is a good model. And you can go again, check out the different models that Pinecone has hosted. Again, I'm not going too much into the different embedding models. That's an NLP topic, which we can look into later in a different lecture, right? And then parameters. And again, I'm using the default parameters that Pinecone gives you. Because I am passing in a passage. It's a simple example. So I'm passing in a passage. So parameters are basically, and actually it's not this way. It's a, so, and truncate in, right? So what I've done here is for the data, what this will do is each instance of data will be D because it's a list of these objects, right, with text and the index. So for each object in that, it's going to extract the text component, and then it's going to create a list of those texts, right? And so inputs to Pinecone's embedding model is basically just a list of these texts, right? And it's going to run the multilingual E5. And what I'm going to do is I'm going to say return embeddings of data, right? I just return that. And so we are good. Now what I'm going to do is I'm going to add a small, well, we've got PCH. Let's just see if it's able to generate the embeddings, right? So we're going to say embeddings is PCH dot generate embeddings, and we're going to pass in data, right? And that should give us the embeddings. So let's run that. Again, I haven't run. Each time you have to run the client, and it's still not got a generate embeddings. Why is that? Jeff generate embeddings. Do I have a spelling mistake here? Oh, I haven't run this again. So okay. So it's generated the embeddings, and let's just print the embeddings. And you see what it's returning, right? The embeddings are a vector type, dense, the values. So now actually if I run the whole embeddings here, if I just print this, let's just rerun this, rerun the data, rerun the Pinecone adapter, and then I run that again. So what Pinecone returns is this object, right? Which tells you the model, tells you the type of vector, and then the data, which is got the type of vector again, and then the actual vector. I'm just returning embeddings.data, which is returning just this piece, and it's telling me how many tokens I've used. So it's giving me this piece, and that's all I need, right? So I'm just returning. Okay, so I'm going to take this out. And I'm going to take this out from here as well. You know what it is, right? And I've already printed it out there. So let's just take that out. So what's next? Now that we've generated our embeddings, so we have a way to generate our embeddings, we can do one more embedding, which is let's just, let's just do the creating an index, right? So we're going to create the index, right? What do you want to pass in? You want to pass in the index name, which now I'm just saying I'm going to call it default because you can create multiple indices, right? For depending on if you have different problems or different pieces of the problem, what's the dimension of the vector that you're creating the index with? Because you could have vectors of different dimensions, right? Depending on the model. We saw in the lecture how if it was just glove, you would have 100 dimensional. In this case, this is going to return vectors of dimension 1024. And so I'm defaulting that to 1024, right? You could have vectors of size 512 and the metric, which again, you have to keep in mind, try and make sure it's relevant to the embedding model you've chosen. In this case, cosine will work well for us. And so if spec is none, we're saying and so we are running serverless spec, which is a real Pinecone and improvement, which means we don't have to do any provisioning. It's very easy to set up, and we're saying run on Pinecone cloud is AWS. So we're running on AWS. You have other options, and the region is US East 1. So it's just creating that specification where the index needs to be hosted. And then I'm going to say if Pinecone does not have that index, right? Because if it already has that index, you don't want to recreate it, right? That's a problem. You're going to say if index, right? Right. And the name is index name, right? The dimension is dimension, metric is metric, and spec is the spec, and that's it, right? You're basically done. And then what you want to do is just make sure that this is created. We'll add a small what this is going to do is it's going to run what is called describe index. And if it can't find the description, it means the index is not yet ready. Meaning if it can't find that the status is ready, So if it can't find that the status of the index is ready, so if it can't find that the status of the index is ready, what it's going to do is it's going to sleep again, check this again till the index you've created is ready. So that should get you set up with an index. When you create something, you should have the ability to delete it. So delete index. Now, ideally, you don't, once you've created an index and it's for an actual problem, you don't delete it unless you're done with that problem. You don't need the index anymore. Right. Okay. So that should be that. Let me, okay. So we have got this index that we can create. Let's go create the index, right? Let's go say, okay. So what is the index we are creating? We're saying create an index. We're saying index name is vector db's demo, right? The dimension, vector db's, yeah, demo. I'm going to call it demo one. Okay. And then dimension. And we've said the embeddings are 1024. So we're going to use 1024. The metric is cosine. And we're not going to create serverless spec. So let's keep that. Let's run that. And then what I'm going to do now is let's insert the vectors, right? So insert vectors. And what do? You say you specify the index, you specify the dimension. You specify the, oh, I haven't created the index, right? Sorry, that's my bad. I got caught up. So first you create the index, right? And what do? You say index name, say dimension, and you say the metric. So let's see if Pinecone can create it. Again, I have to rerun the adapter. So it has the create index. I recreate this. I'm not running the embeddings again. I'm just going to say create index, and it's going to keep trying till it can create the index. So you're going to have to wait for a second to hopefully, till it hopefully creates the index, and it has, right? So it's run successfully. We've got the index. What do we do now that we have the index? Let's insert the vectors, right? So we don't need to do delete. What I'm going to do is add this whole delete here, where we're going to simply ch delete, so that at the end of this session, we can delete the index, right? Okay. So now what do we need to do? What we need to do now is insert the vectors. So let's create the insert function. Okay, let's now create the insert function. So we're going to say insert vectors. Now, what do you need to insert? You need which index you're inserting to. And you can do a smarter thing here, which is you can have a select index function, which just selects the index, and then the rest of the insert, delete, and so on for the vectors uses that index. I'm just keeping it where each time you're giving it an index name, it's going to go pull that index and then insert, delete, or do whatever, right? Okay. So index name, you're giving it the data, which is kind of so that you have the ID and the metadata. And you have to give it the index, the embeddings. We're assuming that embedding 1 in this list corresponds to the data point 1 in this list of data, right? But we're keeping them separate. It's just easier to combine it while inserting. And you give it a namespace, which is a way to kind of, have all your similar vectors in one namespace. So it's an easy way to kind of organize your data. So first, let's go create the index. And so you say self.pc.index. This is just to get that particular index. And then what do? We say, okay, now I need to insert. So what is the command to insert? It's insert dot upsert, index dot upsert, right? And you have to pass it a set of vectors, which I'm going to call records, because it's not just the vector, it's also the metadata and the ID, and the namespace is the namespace. Now I can't run this because I haven't created the records. So let's create records now. Records. What you're passing in is a list, right? And that list has objects that have these three parameters. It's got the ID, it's got the vector, which you call the values, and then it's got the metadata. right? Okay. So where's the ID? Well, it's in the data. So we're going to say D ID. The values are in the embeddings, right? So we're going to say E values. And we're going to say metadata. Metadata is again, a Python object. And what we're going to do there is we're going to say text, right? Or a dictionary. So not necessarily just an object. And you can say the text, right? You can also say, you can add other values to this dictionary or object, right? You can say it's got say class or genre or whatever, depending on the example you're using. And where do I get this D, E, and D? Well, it's actually, I'm going to say, well, I need to extract that from data and embedding. So I'm going to say for D, E in zip data embeddings. If you're not familiar with zip, we'll put out a small video on how the zip function works. I'll add a link to that, so you can go check that out. But what it will do is take these two lists, and they're iterables, right? You can iterate on them. It's going to convert them into one iterable, and D is going to be each value, for each iteration, D is going to be one value from data. E is going to be the corresponding from the embeddings, and from D, which is the data, we're extracting the ID and the text. For embeddings, we're going to take the values, which is the vector. And that's it. You have inserted your vectors. Now, what happens when you insert? Well, you can say the database now has those vectors. So let's go do that. Let's say pch dot insert vectors, I believe, and we have the index name, which we've already set up. We've got the data, and we've got the embeddings, right, which we've already created. Now you could, instead of using the Pinecone thing, you could use some other vector embedding model, sentence embedding model, like sentence transformers. So let's go run that. Again, I keep forgetting to reinitialize this. So I have an error here, which is I haven't put the commas here, which is my bad. I'm sorry. We've done that. Let's rerun this. Let's create the adapter again. And we don't need to create an index or anything. We just run the insert. So insert is done. Let's now get to the fun part. Let's now see if we can query this index with vectors, right? So we're going to say create a query. Now, again, I need to create an embedding for this. Now, the embedding model, like, you need to use the same embedding model for the query as you would for the vectors, right? That you've inserted. Otherwise, it won't work. And as we know here, it's going to look for the text. It's going to take in a list of data points, and it's going to look for text. So even though the query is just one thing in this one value in this case, I'm going to obviously going to say it's text, and the query is exactly what we saw in right. So I'm just asking it a question, basically, right? So what do? You first generate the embeddings. We know how to do that. Embeddings is basically PCH to generate embeddings, query, and we're going to call this query embeddings. Once you get your query embeddings, what do? You say pch dot query, and what do you pass it? You pass it the index that you want to query, and you pass it the query embedding, right? And then you tell it how many nearest neighbor matches you need. Good. Can we run this? No, right? We haven't written the query function. So let's go write that now. But you now see what the query we want to pass in is. Let's now use the query function, and Pinecone will query this index. So what do we need again? We need the index name. We need the embedding of the query. You need the number of neighbors. Now I'm going to default that to 3. We've seen that in this case, we want 4, right? There's a reason for that. This is the way I've set up this example, right? So, and you give it the namespace, which for now I'm just saying is the default. And then you say, okay, index, again, same thing, self.pc.index, and you give it the index name. So you get that index, and then you say index, index dot query, right? And what do you need to pass it? Well, you need to pass it the namespace, right? You need to pass it the vector, right? The query vector. So the vector, which is the query embedding. This is just the query embedding? No, right? We want the actual vector. So we're going to say 0 because if you remember, the query embedding function just takes in a list and returns a list of embeddings, which is what Pinecone returns. So we've got a list. We've only passed it one value. So I want to take out just that value. And what else do you want from there? Well, Pinecone stores in that object that's returned, it stores the vector in the field called values. So we're going to return values. How many nearest neighbors do we want? We want how many ever we are asking it for. In our case, we want 4. So top K. And then what do you do? You say include values, which will return the actual vectors. We don't really care about the vectors as of now, because visualizing it, we could already visualize it, and it's not really going to help us. What I'm going to do is say include the metadata. So we ask it a query and let's see what answers it gives us, right? So what do? We want this to be stored in results, and we return the results. That's it, right? Let's hopefully I haven't added any bugs to this. I've forgotten a comma, I guess. Yeah, actually I've written this twice. Let's fix that. Okay, let's reinitialize the Pinecone adapter. And now let's query it. The vectors are already in. We're using a serverless spec on the cloud. We don't need to worry, just run this line and hopefully it will go generate the embeddings and then return the answer. Now I've used query embeddings here. I've said query embedding here. Let's rerun that. So I don't want to generate the embedding again. Comment that out and rerun the query and see what gives you. And you see what Pinecone gives you. So it's very interesting. That's why I've used 4, right? It says, I've asked it about the movie Matrix. It's very smartly said, okay, first one, the Matrix is a 1999 science fiction film. 2, the movie The Matrix explores themes like. 3, the Matrix follows Neo, a hacker. And then the last, it now brings the 4th one, which is now about linear algebra, right? Now the scores here you see 0.88, 0.88, 0.85, 0.82. So it's not very far away. Why has it done that? There's a reason for it, right? In this 4th sentence, if you see, I haven't used the word the movie The Matrix. I haven't used the word the Matrix. So actually this 4th sentence is part of this para on Matrix, but it doesn't say anything about Matrix. It doesn't use the word, it doesn't, so it's just its effects and action scenes. And because I have made this a separate vector, this vector doesn't seem to have anything to do with Matrix, right? Because the word doesn't show up here. If I'd used this as a continuation with this, so I'd combine these 2 sentences, then the whole thing would show up, right? But it hasn't. That's why I wanted to show 4 vectors. So what we're going to do now is we are going to say, well, that's good, but how do I fix this? Maybe my data is a bit off. What we can do is we can say, I want to modify the vector. It's a database, right? So let's add a small function that says in this Pinecone adapter that says modify vectors. Right? And now what do you want to do? Well, you want to say self, you want to give it the index. You want to give it the ID of the vector you want to modify. That's why that comes in useful. You want to give it the value that you're changing. You want to give it the, which is the vector, right? You want to give it the metadata, right? Because you could keep the vector value the same, but say actually the metadata is wrong. Or you could do something different. You could say actually the vector itself is wrong, the metadata is right. You could do that as well, right? You could change that. In this case, we are going to actually change that sentence and we're going to change the metadata, right? So the metadata is gone. We're going to change it and we're going to change the vector, not sentence, sorry. So first again, we're going to do the standard thing. We're going to get the index. And so like I said, this kind of getting the index, you could have another function that says set index, which you could give it the name and it could set it. And you could just query that index for each of these. That would be more efficient. You'd be calling less, you'll be calling Pinecone fewer times. For now, I'm going to leave it like this, right? And so I'm going to say index.update, which is the way to do that. and you're going to say ID is ID. You're going to say values, and you're going to pass in the values. You're going to pass in the metadata. So set metadata should set the metadata, and the namespace should be the namespace. And that's the modify vector, right? And let's go reinitialize that, reinitialize the adapter. And we're going to now write the modify function, right? Okay, so let's just do that. Give me a second. Okay, so just making sure I'm doing this right. Okay, so the updated text is the effects and action scenes in the movie, the matrix made it a cultural icon, right? That's what do we do? We need to create the embedding. And so we're going to say PCH dot generate embeddings, right? And what does it take in? It takes in a list, and each item in the list has a field called text where we pass in the updated text. So that should generate the new embedding. And once we do that, let's just make sure it's generating an embedding. So let's run that. Hopefully that, yeah, okay. So we've got a new vector. And then I'm going to say, okay, PCH dot modify vectors. What do I need to pass? It index name, which is not changing, the ID, and in this case, the ID was V8, right? You can use more complicated ID if you want. I'm just keeping it simple. So it's V8. So the ID is V8, right? The values, which in this case is the new embedding. And so I'm actually going to extract new embedding. I'm going to say it's a list of 0 and it's values, because now you are kind of passing it the exact vector. And the assumption here when I've written this is you're modifying one vector and its metadata at a time. You're not doing this in batch. So the ID, the value is the actual vector, and the metadata is the actual metadata, which in this case, the metadata is going to be in this format, right? It's going to be text, t-text. So we're going to have to pass that in as well. We're going to say, okay, values and the metadata. And so the metadata is a little complicated. So let me just write something here that says metadata is equal to, well, I guess not that complicated. And the text is the updated text, right? And so I'm going to say pass that in and then enter. Good. So let's go and run this. Of course, there's been an issue because it says namespace is not defined. And that's because I've got a typo here. As always, sorry about that. Let's rerun this. Clearly, I'm typing a bit too fast. And it's gone and modified it. Let's now, what are we going to do? We're just going to go rerun this query. I could rerun it right there, but I want to keep that history of what we did before. So let's just rerun that again. And now The Matrix is a 1999 science fiction film, the movie The Matrix seems like, and this never showed up before. It's actually now got a 0.86 score. The effects and the action scenes in the movie The Matrix made it a cultural icon. And then this was already there before, right? So it's actually inserted it now. It's when it's querying it, it's actually somewhere here now. And this is now going to be the fifth, which we have not looked for. We want the top 4 matches. So by modifying, we've modified the vector and the value, we are able to query this again. So that's very good. Now we're going to do one more thing, which is we are going to, like I said, if you can create something, you should have the ability to delete it. So we're going to say delete vector, right? So let's just add the delete vector. Now that, as you can imagine, is not that complicated. right? What do? You say specify the index name, and then you give it the vector IDs, you give it the namespace. And in this kind of example or demo, I haven't really used namespace a lot, but we still give it the option, right? Okay. And so again, we're going to use index, and that's why I said having a set index function might not be a bad idea. But this is, I guess, more general if you have a lot of indexes and you just want to maybe modify one while deleting the other and updating something else and so on, right? And then you say index.delete, and you can give it multiple IDs, right? And give it the name space. Hopefully no typos. And so I'm going to say delete vectors, right? And that would be that. So let's go and rerun this. Update our adapter again. But again, because we've set it up this way, we only need to, once we reinitialize the Pinecone API, we only need to call it once. So we don't need to call all the other functions. It's on the cloud. I'm going to say the vector IDs that I'm passing. In this case, is just what we've created now is V8, right? And I'm going to say pch.delete, delete vector, right? And I'm going to say index name, and I'm going to say the vector IDs. It's delete vectors, right? Let's run this, and it's deleted. What are we going to do? We're going to run a query again, the same query. And again, I'm keeping the history, so that's why I'm keeping it separate, right? Just change this to 5 and see what happens. And you can see that it's not showing up that index, right? So that index is gone. That V8 is gone, right? And it's only giving me the others. See that the delete has worked as well. And so we've, in this example, fairly quickly, we have kind of created this adapter that allows us to take the data, create the embeddings, and you're now seeing how you can create an index, you can add vectors, you can query them, you can modify them, and you're seeing how the matches that Pinecone generates, basically the database, the vector database, and if any other vector database should do the similar thing, where it should, you see how the context is kept when you have in the text something about matrix, it's able to retrieve that. And if it's in context with the movie, when you don't use the word context is wrong, it's not going to retrieve that. We've seen how you can now modify the database, right? And of course, you can delete something from it as well. Now I'm going to delete the index at the end of this. And so we've cleared up, what we've inserted. So that index is gone. So hopefully this kind of hands-on tutorial, quick tutorial, the idea was just to give you an idea of, in practice, we've kind of covered the theory of semantic search. We've understood how that worked, what the pieces are, and so on. We now get a hands-on idea, a feel for what we're actually doing, right? When we have some data and, how do you generate an embedding quickly? You can use different models, but you see the basic idea. And then if you use a vector database, what's the basic idea? We've used a hosted, Pinecone version. We've used serverless, so we are not worried about how we're deploying it. The idea is to show you how it works, right? And how you can now kind of add data, and you have the vector, you have the metadata, and now when you query it, you can get contextual responses. You can modify your index basically, and you can again requery it. So as you insert, as you modify, obviously the database will give you interesting matches. You can use a different vector representation and redo the entire thing. Just remember that the vector embedding you use to create the vectors that are stored, you need to use the same embedding model when you query, right? That's it. You can modify this now a little more, maybe if you want to do more interesting things. Like I said, keep the index, maybe here, do the indexing, do the embedding generation in the query itself if you want. I feel this is slightly more general. But hopefully with this lecture from start to finish, you've got an idea now of how we've kind of understood the idea of vectors, what a vector embedding is, and how it captures context, which takes us nicely to semantic search. And then you've understood how that works, the idea of nearest neighbors and approximate nearest neighbors, and how a vector database uses an approximate nearest neighbors as its indexing mechanism to allow it to quickly search through vectors. And as a result of that, now you can store text or images or anything else in vector form. And now when you query it, right? Depending on how good your embedding model is, the database can quickly give you, responses of the nearest vectors. And as a result, you could have a very smart search system, right? So whether it's building a search engine or, using this as the memory for a language model or a RAG model or something like that, doing something like document search, vector database is a key part. And hopefully now you're in a good place to keep going. Now, in the next two lectures in this series, we're going to go a little more into the algorithms, right? We're interested in how how the HNSW, for example, works and so on, how the nearest neighbors works a little more. We'll look into that a little more. And then we'll kind of come up with a slightly more complex application to demonstrate a little more how you can use the vector database in practice. So hopefully you've enjoyed this lecture, you've learned from it, you're finding it useful. Stay tuned for more.